This is another lecture in the FOA series of lectures on fiber optics. In this lecture, we want to teach you how to talk fiber optics. Because with every technology, you have to understand the jargon, the language of the technology, and all the strange words that are special to that particular area of technology. So after you go through this video, you should understand the language of fiber, and it will help you if you're taking a class or studying on your own or talking to a customer or a supplier about our crazy technology. You need some basic knowledge to talk fiber. You need to understand the jargon, the special terms that we use. You need to understand basic fiber optic technology, and you need to know what the components are and the networks are and how they're all used to create communication systems. This is needed for those new to fiber optics or those who are not FOA certified, who are taking specialist courses that expect you to know these terms and know our language. Fiber is, of course, the backbone of the world's communication systems, connecting us up on submarine cables that connect all the continents, landlines across the land in every continent, and connecting even wireless towers. Practically every application that communicates with data anywhere in the world is going to be connected on fiber. So it's important that you understand what we talk about when we use the language of fiber optics. This photo, taken by AT&T 40 years ago, shows how a single fiber would carry more communication signals than that large multi-pair copper cable. Well, today, a single optical fiber would carry more communications than 1,000 of those cables would 40 years ago. The whole economics of fiber is determined by the fact that it has higher bandwidth and higher distance capacity. It can go further and faster for a lot less money. When you compare communications media, you understand the value of fiber. Wireless, down at the bottom on the graph, is the slowest because bandwidth is scarce. It's hard to use. There isn't a lot of radio frequency bandwidth. Copper wire is simply limited by the physics of sending electrical systems over twisted pairs of wire. Multimode fiber, which you'll learn what that means in a second, gives you another 10 times more bandwidth than copper, but single mode fiber gives you almost unlimited bandwidth, more than a terabit per second. And then on every one of those single mode optical fibers, we can put signals at different wavelengths of light, up to 128 different wavelengths today over one optical fiber, which means we're not talking about a terabit per second, we're talking about more than 100 terabits per second. And that's why fiber is used for every kind of communication you can imagine. And by the way, the term you learn here is wavelength division multiplexing. The optical fibers we use for communications are about the size of human hair. Most of the fibers are made completely of glass, molded as a single structure incorporating a core and a cladding. But some fibers are also made out of glass and plastic, or even all plastic. The fiber transmits light in the core of the fiber. The light is trapped in the core by the cladding using an optical technique known as total internal reflection, which traps the light in the core. On the outside of the glass fiber, we put an acrylic plastic buffer coating to protect the fiber from moisture or damage. There is some FOA materials on how fiber is made, which you might find interesting also. There are three basic types of optical fiber that you will hear us talk about. Multi-mode step index fiber, shown at the top, just has light bouncing around inside it to carry it through the core of the fiber. Graded index multi-mode fiber, however, guides the light with a special core design that ups the bandwidth 100 times faster than multi-mode step index fiber. But single-mode fiber restricts the light to one ray of light going straight down through the center, and that's how it gets much, much higher bandwidth than the other multi-mode fibers. We use cables to protect the optical fiber when we install them in the real world. Indoor cables have to meet flammability standards so that they don't cause or contribute to fires. Typical types used in indoor cabling are what we call tight buffer cables, like the zip cord at the top, the distribution cable in the center, and the breakout cable, which is just a large number of simplex cables down at the bottom. Outdoor cables must be much more rugged. They have to be able to be pulled or buried or installed aerially and to withstand the environment in which they will be installed. The common types are what we call loose tube cables, the cable at the top, where the fibers are enclosed in a small plastic tube. That cable can be armored, as the cable in the center shows, to protect it from damage after it's buried directly in the ground, and that includes damage by chewing by rodents, because they love to chew on the jacket of the fiber. Ribbon cables lays all the fibers out in a ribbon and creates a cable that has much, much higher density, that is to say, more fibers in a smaller cable. We have two ways we can join fibers. We can join them permanently by making a splice. Most splices are made by fusing the fibers in electric arc, welding them together basically. But we also use mechanical fibers that align the fibers and crimp them to hold them in place. We use these outdoors for long cable runs to connect cables, or sometimes to connect indoor cables to outdoor cables when we have to run a cable into a building. We also need temporary ways of joining fiber for patching cables together and for connecting equipment. And for that we use connectors. These are the most popular connectors. The beige connector on the left is an SC. The metal cable in the middle with a bayonet clicking nut is an ST. And the push-pull locking connector, the very small one on the right, is an LC. These are the connectors you will see most often in the marketplace. To transmit signals over an optical fiber, we use converters that convert from the electrical domain to the optical domain. We call them transceivers because they are transmitters and receivers typically in one module. Some transceivers work over two fibers, transmitting in one direction on one fiber and the other direction on another fiber. But some other systems, like the fiber to the home systems, often transmit in both directions over one fiber. Inside the transceiver, we have a transmitter that has an electronic interface that accepts an incoming electrical signal, converts it to an optical signal using a light-emitting diode or a laser, and couples it into an optical fiber. On the receiver side, we have a detector, a semiconductor device that takes an optical incoming signal, converts it to an electrical signal, and then we have an electronic signal interface that conditions the outgoing signal for the electronic circuits that the transceiver is connected to. There are two major performance issues with a data link. One is loss, the loss of the optical signal as it travels along the optical fiber, being attenuated by the fiber and by any connectors or splices in the link. We must have a sufficient amount of power at the detector to get a good signal transmission. To ensure this happens, we look at the design of the data link and do what's called a power budget to make sure that our transceivers and our fiber optic cable are compatible. The second problem we have in signal transmission is dispersion, that an optical signal gets spread out by the characteristics of the optical fiber that's transmitting it. We must ensure that for every data link that the signal at the receiver is such that each individual pulse can be distinguished by the detector in order for the signal to be transmitted properly. Dispersion is a problem in short multi-mode links and very long single-mode links. There are two major classifications of fiber optic installations. What we call outside plant is just that, it's outside. It's mostly aerial, underground in conduit, or direct buried. Although, of course, all of those submarine cables are what connect all the continents in the world. Indoors, we call fiber optics installations premises cabling. It can be in computer rooms or telecom rooms, cables running between the two, or running to things like surveillance cameras or Wi-Fi access points, or any other kind of equipment inside a building. Once we install our fiber optic cabling, we test it. And one of the first things we do is inspect all the connectors with a microscope. We're looking for dirt, scratches, contamination, or damage. A microscope is one indispensable tool for every fiber optic installer and every fiber optic user. And the reason we say that is because you can look at a connector and tell if it's good. Another valuable tool for fiber optic testing is a visual fault locator. A visual fault locator uses a high-powered visible laser, which we inject into the fiber, and it allows us to trace fibers and find faults by light leaking out of the fiber, as you can see in this photograph. We mentioned earlier that optical loss is an important performance parameter, and we typically measure optical loss with a light source and a power meter. A light source is like the transmitter of a data link, and the power meter is like the receiver. And we can calibrate these two together and measure the loss of the cable plant to ensure that the cable plant will work within the power budget of the data link that we're using over that cable plant. We can also take a snapshot of our fiber optic cable plant with an instrument called an OTDR. It works sort of like radar, sending a signal out the fiber and creating a picture of the loss in the fiber and where events like splices and connectors are. OTDRs are expensive and a bit hard to use, but they're highly valuable tools to diagnose problems in the cable plant. We also often, on long distance lines, take that snapshot and save it in case we ever need it in the future to diagnose problems or to restore the cable plant. This video is just a short overview of the main jargon that we use in fiber optics to help you understand when people are talking fiber optics. But there's a place to go to learn more. There is on the FOA guide a page all about the jargon of fiber optics. And what you should do is pause this video, write down this web address, and go there. And you can get a lot more jargon information that the FOA has made available on our online reference guide, where you'll find almost 1,000 pages of technical information. The FOA provides lots of other ways you can learn more about fiber optics. We have more than 200 schools around the world teaching the FOA curriculum and offering FOA certification. We have about 80 videos on our YouTube channel. We have free self-study programs online at FiberU. And we have Lenny Lightwave's Guide, which you can download as a free iBook from Apple's iTunes, or you can go to lennylightwave.com and download a PDF version. The FOA provides all of this information to the world to promote professionalism in fiber optics. We're the Fiber Optic Association, the international nonprofit professional society of fiber optics. Here's how to contact us. Let us know if we can help you.